Alright, so in this video I'm gonna be explaining this paper with the title Retgk, graph kernels based on return probabilities of random walks. There are many kind of graph kernels like WL kernel, graph-led kernel, random walk kernel, and what else? Shortest path, for example. But this random walk kernel is computationally expensive, especially for large graph. Shortest path graph is good. There are the node label, edge label version of that is also possible. But WL kernel only node label. You should have node labels, and so each one has pros and cons. But this paper in 2018, NeurIPS 2018, wants to talk about how to create graph kernel based on return probabilities of random walks. You can design your own graph kernel with such heuristics like return probabilities or hitting time or anything. Graph structured data arise in wide applications such as computer vision, bioinformatics, social networks. Quantifying similarities among graphs is a fundamental problem. So we develop a framework for computing graph kernels based on return probabilities of random walks. The advantage of our proposed kernels are that they can effectively exploit various node attributes while being scalable to large datasets. So we conduct extensive graph classification experiments to evaluate our graph kernels. So I hope you are familiar with random walk on G, which is a Markov chain, like the words in a sentence. So we have some transition probability when we go from one word to another word. So we measure it like this. And the return probabilities. So we compare two graphs by quantifying the difference between their transition probability matrices. However, big technical difficulties exist since the size of two matrices are not necessarily the same and their rows or columns do not correspond in most cases. To tackle the above issues, we make use of the S-step return probabilities of random walks in G. To do this, we assign each node, V sub I, an S-dimensional feature called return probability feature. So this entry is the return probability of S-step random walk starting from V sub I. Now each graph is represented by a set of feature vectors. Because, for example, each graph has n nodes, then we have n feature vectors. Because each feature vector has return probability to each node. And the proposition says that if G and H are two isomorphic graphs of n nodes, and then this satisfies. So this is a toy graph on the left, and B is the S-step probability of nodes C1, C2, and C3. These points. This node, and this node. If you look at their S return probabilities, it's very interesting in this toy graph. For example, 200-step return probabilities, or S could be anything. The nested graph figure is closed-up view of the rectangular region. So the y-axis is return probabilities along the x-axis, which is random walk steps. So as random walk steps increases, the return probabilities decreases. And it has an interesting relation to eigenvector embedding, which is a popular way of graph embedding everyone knows, using the eigenvectors of just the Laplacian. And so to compute this return probability feature, which we need for return probability graph kernel, we write this matrix multiplication like this, because the brute force computation requires this amount of matrix multiplication. So this is the time complexity of that, which is very high, especially when your S is huge. But since only the diagonal terms of transition matrices are needed, we have efficient techniques. We can write P like this, and because B sub G is symmetric here, and then it can be, for example, if lambda k and uk are eigenvector and eigenvalue and eigenvectors of B sub G, then the return probabilities has this interesting explicit relationship. So we can obtain all nodes as a step very quickly, because the eigen decomposition just requires order of n cubic. And if the graph node number is large, the eigen decomposition is relatively time consuming. To make it scalable to large graph, we use Monte Carlo method to simulate random walks. And also Hilbert space representations of that and some properties of them, and approximating Hilbert space embedding of graphs. And we do it for different data sets.